20 minutes before break. Before we carry on, I thought, given the conversation that you've had over the break, do you have any other questions? Or what kind of burning questions were there around the things that we spoke about in the past? We spoke about model, inference, and algorithm paradigm, and I gave you some examples of convnets and maximum likelihoods, or latent variable models and variational inference. Around those foundations and principles, were there any other questions that appeared, a clarification that you need? Otherwise, we'll carry on and do something. Was there anything? I'm just going to pour some water while I let you think about that. Okay. So I want to just start with the next bit, which will just be, this is going to be a session on a little bit of mathematical statistics. And we're going to build up a set of tools for you to later on use in the other lessons of the course. And so I call this second part just tricks. And there are some foundational tricks that I think that if you have them, you can always use them to do lots of interesting manipulations and come up with new tools and new approaches for solving problems. So let me just reset this. So I have two objectives here. I have 6 tools for you for manipulating probability distributions and probability questions. So we're going to use these 6 tools to unpack 6 different tricks, and these 6 different tricks are pretty cool, I think. And you can then use these tricks to sort of create new kinds of things. And then I have a second one, which is about building connections, as we have been doing between machine learning and other parts of computational sciences, whether that's neuroscience or economics or psychometrics. So I'm going to remind you a little bit again about these different kinds of inferential questions that we might have. So I always talk about this idea of probabilistic dexterity. I want you to be so flexible that you can jump around and manipulate probabilities just by looking at them. And if you have this kind of probabilistic dexterity, then all the fundamental problems of machine learning are sort of yours to tackle, yours to unpack, and yours to innovate upon. And there are many different kinds of inferential questions that are going to appear in many parts of machine learning. So the one we mentioned was this idea of evidence estimation. If I have a data point, observed data X and other variable Z, they may be parameters or unobserved variable, can I know the probability of the data, the evidence of that data? I may want to know something more than the evidence or something other than the evidence. Those are the moments. I may need to know the mean, the variance, other higher moments. Can I do the moments? The moments are computed as an integral of a function against the distribution that we are interested in. And usually the moments are linear, quadratic, cubic functions going on in this way. And you can do all those polynomials, higher order polynomials, and you'll recover the whole distribution. So moment computation is pretty important, and this is one that you'll see lots of over the next few days. Parameter estimation is another one. If I am given a set of data from 1 to n, how can I know the distribution of the parameters of my model given the data? Then you have other tasks like prediction. If I have seen a set of past observations, a past time series, how can I make predictions about how that time series will look into the future? Can I make predictions of other sequences in the data point? Planning is one I mentioned a little bit about the end around decision making. If I have a cost function t, or c in this case, at a particular time point, how can I know or maximize the average cost or look on average behavior by taking a set of actions u? So this is a very fundamental question. When you do when you come to reinforcement learning, you'll see this integral written in a slightly different way. Then there is the question of hypothesis testing, that statistical operation of doing comparisons. How can I compare a hypothesis 1 to a hypothesis 2 and make a statement about goodness of fit, usefulness, etc. And then experimental design, which maybe you saw a little bit this morning. If I have a set of designs, or I need to understand a set of experiments, the next kind of sequence of actions that I'm going to take, given a past set of experiments, how can I use the fact that I'm gaining information to decide which experiment is the best and the right experiment to do? So these are all. One of the things you will see, there are several commonalities between all of them. They're all obviously based on manipulating probability distributions. The probability distributions are all high dimensional. They are not univariate. They're all multivariate over high dimensional thetas, high dimensional actions, high dimensional observations, a time series which may be infinite, which may be infrequently sampled. And there usually lots of them involve integrals. There's an integral here. Inside here is an integral. Inside this divergence there's an integral. And so a lot of the tricks are around manipulating integrals. So we're going to do maybe just the first of these tricks before we take a break, so you get a bit of a flavor of things. So the first trick is called the identity trick. And the identity trick you can always use, because this will be the number one problem you will get. You will have an integral of some probability distribution, and you want to change it into an integral of a different probability distribution. So that's what this trick is about. I want to transform an expectation with respect to distribution P into an expectation with respect to a different distribution, distribution Q. So let me write that out. I have an integral of P of x times f of x. So I'm integrating the function x under the distribution P. I'll write that using the expectation notation. It's expectation under P of f of x. I would like to instead have a different kind of expectation, the expectation of a different distribution Q of x of some modified function. Again, if I write out the integral, it's the integral of the modified function g, which may be itself a function of the original one, times the new distribution Q. And I want to have some way of going between them, and the way you go between them is to multiply a 1. You're just going to multiply and divide by P of x. Nothing about the probability distribution is going to change, but a lot about its interpretation, its expectation, its even statistical and numerical properties will change just by manipulating this one. So let's do a little bit of that. So here's the integral problem. I have a latent variable z, or some random variable, doesn't matter, it could be observed, and I have another random variable x. And this is I'm going to give a causal direction so we can write the conditioning. This integral problem is to compute the evidence, P of x, integrate the conditional distribution, P of x given z, times B of z, and integrate z. Z is again high dimensional distribution. So, do the identity trick, multiply by 1. Nothing has changed in that integral. It's exactly the same as the one before, so the evidence is unchanged. Now, just let's regroup the terms. We're going to regroup Q of z and P of z. So I'm going to add this ratio, P of z divided by Q of z times Q of z. Now, there are some conditions going on, but let's just do the final step. This is now a new kind of expectation. This is the expectation under Q, this distribution, times this product, P of x of z times the ratio P of z divided by Q of z. So I just want us to look a little bit at what's going on here. Because I'm dividing by something, division is a very dangerous operation, so we should try to avoid it if we can. Unfortunately, here we can't. So if we're going to divide, we need to make sure that we never divide by 0. So the first condition of using this kind of identity trick, and everywhere you will see it, will be this line, that the support Q of z is always greater than 0 when the other terms it is being, the numerator is not 0. And that's a simple statement that we always assume. And sometimes you will actually have a failure of this in your code, in the actual problem, because the support of the distributions where the actual data lives is different, and then you will see nans blowing up, gradients going to infinity, these kind of things, and then we have to do some other tricks. But usually this is sort of the source of that problem. So usually do give a bit of check, add a bit of tests in your code just to look at the ratio. I want to talk a little bit about this ratio, which is P of z divided by Q of z. Ratios like this are also one of the most fundamental probabilistic quantities you can get. Because this, if you read the integral, it says something very interesting. I can take the average over Q of this distribution P of z, but I just need to multiply by a correction factor to get the probabilities correct, and so that everything is the same, and the probability is given by this ratio. And the last trick, we're going to come and look at how to compute this ratio in a different way as the very last trick. So in almost every trick, this kind of ratio is going to come up, which means this condition is going to come up. So it's sort of, we have to think about that. And then sort of Q of Z, the way I've written it here, needs to be something that is easy. The point of doing this trick is that I replace this P of Z, which may be something a little bit more complicated, something I don't want to deal with, to something else which is simpler, which I control, which I know, which I am manipulating, which is this distribution Q. So you usually want to have Q, which is something a bit different. So this is actually the principle of importance sampling. And importance sampling is the first kind of method you will learn in Monte Carlo methods, that you have this integral P of x, which is the expectation under some distribution Q of z times the probability distribution Px given z times the ratio of P of z divided by Q of z. Now, this step I want us to just spend a little bit of time on to understand language and what is going on. This is a different kind of trick. This is Monte Carlo trick. It's the metropolis trick. It says that an integral can always just be computed as a discrete sum, or you can approximate the integral as a discrete sum. Now, when we move the step from the integral at the top to this summation at the bottom, then we instead call that new object an estimator. This object in the green box is an estimator of the integral above. Now, let's just talk a little bit about more. How did I have to do this? I sampled from z's from the distribution Q of z. They are these zs's, which I wrote here. I computed the ratio of P of z divided by Q of z using that set of samples, so I know what the difference in the probability is, that correction factor, and then I compute just the average of the likelihood, this probability distribution under those samples reweighted by that correction factor, and I just take the average. So this is an estimator, and usually all integrals we want to write in the form so that we can get estimators out of them. All the other tricks rely on this sort of concept that we want to get estimators. And the reason I'm going to call it an estimator is that this new object is itself a random variable. It's a random because I sample from z of s, and now I have a set of z's, and I could take many different ways of sampling those z's and computing an average. So this object here is a random variable itself. It has a mean, it has a variance, and so we usually want to look at the mean and the variance of these estimators. So that's what importance sampling is about, and it has many, many different uses. So importance sampling is one way. We'll look at it in another set of tricks around manipulating stochastic gradients and how we compute gradients. If you're going to do a little bit of proof around correctness of a method, then usually this is the trick you will use, because then you can introduce that condition and you can state all the assumptions around the correctness of the proof when we're deriving probability bounds. And this kind of exactly this principle will get used later on in reinforcement learning when we are looking at changing different types of behavior, the behavior that I got the data from the behavior that I actually want to learn. So you're going to see this trick in many, many different places. Let's just talk about the identity trick. Some questions, confusions, or comments around anything around importance sampling, manipulating probability distributions, using the identity trick, and Monte Carlo estimators. Is there sort of a thought? Are you confused? No? Yes? Got it? Mm-hmm. Yep. You always need to, so the key point here is that you always need to evaluate both P, everything must be evaluated. If there's any single term that you don't know how to evaluate, then in terms of an estimator, this is not going to be useful. You won't be able to derive an estimate. You will still be able to use it for the purpose of proof to create probability bounds and for other kinds of manipulations of integrals. But at that point, if you can't do that, then I'll show you a trick at the end to compute this ratio when you don't know how to evaluate the probabilities, but only using samples of it. So I think that's a very important point, that you need to know to be able to evaluate things. There's also an issue of the variance. Another sort of question around what's going on here. Mm-hmm. Yes? So this method is literally used in everything. So let me think of a really good example of where this one comes up. So You may not realize it, but traffic lights have an interesting control problem underneath them, which they look at the ratio of how they're going to do the switch of traffic lights. So this is a foundational problem in queuing theory that you'll study in operations research. And so how they actually, you can write a probability model of a queuing theory. Queuing theory just needs you to do two things. You write the probability of cars arriving at the thing, you write the probability of things leaving at the thing, and you write the probability of things waiting at the traffic light. So these are three probability quantities. Usually one of them is very complicated, and so to get rid of that, you will multiply by this trick, and then you will be able to rewrite a gradient to compute the rate at which cars need to leave the traffic light, and that basically the time, and you solve to minimize the time. So this is basically one very good place. I don't know if any of you know about AlphaGo, for example, the big algorithm from DeepMind that we worked on that solved chess. In the very foundation of that algorithm, how it actually works by assessing different moves is to compute this trick to evaluate the probability of how one thing is different from another using that ratio. So this trick is, at the forefront of what we consider miles and AI in the most mundane thing of traffic lights even. And later on when you see Ulrich and David Bly speak, they will show you this trick which will appear again because it is how you will do all the variational inference, one of the largest areas of inferential thinking that we have today. And then of course, the foundational thing that we know certain things work are because we can derive sort of use the different kinds of bounds to actually show, and we have to use this trick to show that the estimator is correct, that we have unbiasedness, that we have consistency. So it's so fundamental that you won't get like this thing came, but usually queuing theory is one. All of reinforcement learning and control theory uses this trick everywhere. Lots of rules in probability theory. Do you have a question? Okay, so the question was, he's lost the point of like, what's going on with this estimator? If I still need to evaluate everything, why am I actually still computing P of Z, Q of Z? I need to sample everything in the end. Why don't I just sample from P of Z directly and evaluate the integral, right? So there's lots of things to say about this. Let me just start by one point saying, usually, if you want to do numerical methods, so one of the reasons to do this is that we get numerical ways of doing things. We usually cannot solve the integral, and so we want to be able to compute numerically, which is why we want to get to this point of getting an estimator and computing the integral by taking an average over a set of samples. So that point I think you got, because that's very fundamental. We need to always be able to do that. The sort of second point, which is one I can't quite explain to you here, is related to how you compute the integral. So yes, you can certainly sample from P of Z, evaluate Q of X, P of X given Z under that set of samples, and evaluate the integral. This is the most basic method of computing an integral, and this is sometimes being called the worst Monte Carlo method ever to exist, ever to have been created. And the reason is because you want to control the accuracy of the integral at the same time. So one of the reasons to have this ratio of P of Z divided by Q of Z is that there are two things that you are actually interested in when you want to compute an integral numerically. One is that it is accurate, but also one is that it is low variance. And the issue of using Q of Z is that Q of Z gives you a way of controlling the variance of the estimator. You want, of the space of all possible ways of computing an integral, you want the one that is the lowest variance, because the lowest variance one will give you the least computation, the maximum accuracy, and all these kind of things. And I can show you a bit more of a proof offline around when the condition breaks, about absolute continuity and the sort of variance properties of these kind of integrals, and why this is the real reason we're actually doing these tricks. More questions or thoughts around just manipulating probabilities in general even? Yes? Mm-hmm. So yeah, Q needs to be simple, and I'll show you in another trick, maybe 4 tricks from now, a way of making Q a little bit more complicated. So by default, everyone chooses a Gaussian. So again, this depends on the problem. There is one condition which I said was that Q must have support, have probability everywhere where the product of P of X given Z times P of Z has probability. So if the uniform is not going to satisfy that condition, then you shouldn't do that. Then you can't use the uniform because you'll break the condition. So typically, if you are working continuous probability distributions, people use a Gaussian because the Gaussian has support everywhere. But then there is a correct question of how it is you choose the right Gaussian. So the question related to the variance is that the tail of the Gaussian can be very light. So if there are rare events in the data that you're observing, then you won't average the rare events correctly. So then you will want a different distribution to average over. So then you'll want maybe a class of distributions which is slightly more broader, extreme value distributions maybe. So you sort of need to know, am I dealing with rare values? Am I not? Am I working continuous space? Do I have bounded support or not? How can I satisfy the condition of absolute continuity where the probability is greater than 0? And is that really working sort of there's also, I built a model because I want to interpret the model, and Q has an interpretation in this model. And so does that still satisfy sort of what they call phenomenological models, models that represent phenomena of the world, and can I still use that? So there's still some work to do about using those estimators. More questions or thoughts? Yes? So yeah, this is a question is about what are the limitations of importance sampling. So importance sampling, actually, the trick is very easy, but when you want to use importance sampling to compute estimates, the main limitation is the question that was just asked before. How is it that you choose Q? In importance sampling, we call Q a special name. It's called an importance distribution. How is it that you choose this Q distribution? There are other ways of computing the average that are equally effective. You can compute the average through a harmonic estimator instead, so harmonic mean instead. So what are these ways? So one of the key points is choosing the Q distribution so that it's effective for your model, again, because variance of the estimator is the key bit. So if you can't choose a good proposal distribution, then you won't sample efficiently through the distribution, and then you'll just be wasting time, and then you'll have an inefficient kind of estimate. So variance is usually one, and usually this kind of naive importance sampling, as you do, requires many Zs to be done. You need to sample a lot of Zs to get down. It's a Monte Carlo estimator, which means the accuracy of the estimate is going to go down as 1 over n, or 1 over square root of n, like all Monte Carlo estimates. So you may need a lot of samples to compute an accurate average. And you may not want to have a lot of samples because we have computational budgets, we have time, which we are considering about. So it would be ideal if we could get away with a few samples, 1, 2, 3 samples instead. Okay, I think it's lunchtime. We'll do the other 5 when we come back. So have a good lunch, everyone.